Hey everyone and welcome back to PrepFusion. I'm Anish and today we'll start the lecture 3B of this electrostatic chapter. So we have started with Gauss law. We know what electric flux is. We done few questions and the questions that I gave you homework that also I will explain here today. And we'll learn how to use Gauss law using symmetry. Also we'll do the electric field variation of electric field due to finite charge distributions using Gauss law. You will see how simple things become when we want to derive the electric field expression with the help of Gauss law. Okay, and also we learn few misconceptions of Gauss law. So let's go back to first of all the previous questions that I gave you as homework. Okay, I'll quickly go through them and quickly tell you what is the thought process and how we exactly solved them. Okay, I think before this all of this were solved. Before this none of them were remaining. Yeah, all of these were actually solved. Okay, fine. So this was the homework question. This was the first homework question that I gave you. This is a very interesting question. This is like a wedge like structure where I have 5 surfaces. This one, then behind this 2, then at the top 3, this rectangle 4, and this bottom part 5. Okay, I have 5 surfaces. So you have to compute the total flux and also the flux through each 5 surfaces. Okay, so 2 things you have to compute. I will just enter it. So first of all, what is flux? So when these known type of shapes come, right, you just find out the perpendicular area with respect to that particular flux. With solving more questions, you will be able to understand how to tackle these type of questions. So here, first of all, identify I have 5 surfaces. So I have this AEFD. AEFD is what? This AEFD, this surface. This is a rectangle surface. So here, electric field is like the axis they have given is in the plus AY cap direction, and AEFD is what? Area vector of a closed surface will be pointing outwards from that surface. So it is in the minus AY cap direction. So I can see they are just anti-parallel of each other. So I can do the simple computation, simple dot product, right? So electric field I will replace with EAY cap, and the area vector I will replace with the magnitude of the area. What is the magnitude of the area? Do I know the side? Do I know this height? No. I know this A and I know this length B. Okay. So this is the hypotenuse of a right angle triangle. So A sine theta will be this AE length. So I got my AE length. So I will replace it A sine theta. And what is this? Base, this is simply B, right? This is just parallel, so this will be B. So the area will be A sine theta times B. And what is the direction? Direction is minus AY cap, because this is pointing outwards from the closed surface. So if I do the dot product, simply I will get minus EAB sine theta. Remember, I have written this with a sign. There is a reason behind it. I will explain just in a bit. Flux is minus EAB sine theta. Now let's come to this EBCF surface, B surface and DCF. Why are this 0? Because the 90 is because the angle is 90 with respect to the area vectors. If I observe this surface EBCF, this bottom surface, right? Here my electric field and the bottom surface, the area vector is pointing downwards, right? This is outward from the surface. The angle is 90. So obviously cos 90 will be 0, hence flux 0. Same for this particular triangle, right? Here the angle, like this is in the minus this is in the plus AX cap direction, and electric field is in the plus AY cap direction. Again it is 90 degrees. Again this will be 0. Same for this back triangle as well. So not electric field, flux will be 0. Okay, so cos 90 will be 0. That's why all these 3 surfaces flux will be 0. What about the last surface, ABCD, this inclined surface? So in this inclined surface, what is happening here is that the area, magnitude of area is A times B, right? This is AB. Now the electric field is not directly like in 0 degrees with the area vector. It is with some angle. So this angle is theta. So this angle, if I just draw a straight line here, this angle will also be theta. And the surface vector, right? Normal surface vector will be somewhere here. So this whole this surface vector will be 90 degrees from the surface, and this is theta. So this small angle will be 90 minus theta. So exactly this is the angle between the electric field and the area vector. So I have written that electric field into magnitude of the area into the cos of angle between them, that is cos 90 minus theta. Cos 90 minus theta gives me EAB sine theta. Okay, so the flux through each surface I have got. Now the overall flux actually comes out to be 0. So this is like same as telling the same thing as Gauss law. Flux through closed surface will always be 0 if the charge enclosed inside the surface is 0. Here charge enclosed is 0, so the overall flux will be 0 of a closed surface always. Why? Because whatever flux or electric field lines that comes in, it always goes out from the surface. Okay, it doesn't stay here. Okay, so it goes out to, so overall net flux is 0. That's why it was negative flux, because it was coming inside and it is going outside. That's why it was positive flux. So overall flux is 0. Flux through a closed surface will always be 0, only due to outside electric field for a closed surface. If I have inside electric field, then things will change. Okay, so this is again reiterating the Gauss's law. So this is the next question. These questions are very good because these basic questions can actually come. Basically, you have to identify the projection here. So if you identify that flux is passing through this hemispherical surface, not flux, electric fields is passing through this hemispherical surface. So if electric field is passing through this hemispherical surface, how will be the how will the projection be? So if I project this, right, each small areas, it will be just like a half disk. Just try to visualize. If I project each small areas of this hemisphere, it will be just like a half disk. How should I do this? Like here I have a, like, this is just, I don't have a bowl right now. If I had a bowl, I could have shown you, just this is just a bowl, right? This is just a bowl. If I just like project this will just be a disk. If I just project all the small areas, that will just give me a half disk. With respect to the half disk, everything is like the area vector is this, either this or this. I'm not concerned about the direction. I'm just concerned about the, like, in which like what is the angle between the electric field lines and the area vector. It is simply 0, right? It is 0, either in this direction or in this direction, 180 or 0. Okay, either minus or 180 or 0. Okay, either it will come minus or plus. Okay, I will just take the magnitude. So it is 0, hence simply it will be electric field, like D is epsilon into electric field, that is 2, into the projected area magnitude, and cos 0 is 1. That's why cos 0 is 1 here. So I just simply write a 1 over here. Okay, so this will be like 2 epsilon into pi r square by 2. So overall this will come out to be epsilon pi r square. Same thing will be followed here as well. What is happening now? This is interesting. This is very good question. So you have electric field with respect to the reference, it is 45 degrees, it is tilted, and this surface is given. Now what you need to do is, in this type of question, right, one thing is sure, you have to find the area vector that is parallel to this particular electric field, or the surface that is perpendicular to this electric field, and also have to break this electric field down into two components, one in the x component, another one in the y component. So exactly that is what I did. So actually what will happen, there will be two projected surface, bit of the electric field. If I just break it down in this direction, so there is E1. What will be the projected area? Basically the projected area will be basically this disk, right, this full disk. So hence this is a full projected area, and I have a E2. What will be the projected area? Remember, this is the same case, just tilted 90 degrees of the first case. So again, through a hemisphere electric field is passing, and what will be the projected area again? This will be half disk. So this one was full disk, this will be half disk. Okay, so here this will be E into under root 2. Why? Because I have broken this down. E1 will be 45, E1 E cos 45, and E2 will be E sin 45. So E cos 45 is root 2 because E is 2, so it will be root 2, and E sin 45 is root 2. Okay, so it will be epsilon root 2 into pi r square. Okay, this will be equals to root 2 epsilon pi r square. So this whole thing is same only because here again the angle between the area vector and the electric field E1 is 0, because here this, if I compute the area vector, it will be simply either 180 or 0. I don't care about the direction, I care about the sign. I care about the magnitude. Here again the same thing, angle will be 90. Again this area will be what? Pi r square by 2. This will be pi r square by 2, and this is under root 2 because I have just computed the magnitude of E2. Again the angle is 1. So here this will be phi1 plus phi2 overall flux, just simple scalar addition. If I could do this, I will get back this value. Okay, simple things only. Okay, so next is this is another great shape. This is just a cone. Okay, again this electric field is tilted. So whenever this electric field is tilted with respect to the reference, you will break it down into two components, E1 and E2. This time if I break it down into two components, E1 and E2, E1, right, will pass through this curved surface area of this cone. So this will just project like a triangle. This will be just a triangle of height, altitude h, and of base 2r. And again the top E2, right, E2 will just cross this whole disk. So again this will be a full disk. If I compute, again E1 magnitude will be root 2, E2 magnitude will be root 2, E cos 45, E sin 45, and like E1, E2 respectively. Now phi1 will be simply its magnitude, E magnitude, epsilon will always be there because this was D expression, into area of the triangle. Area of the triangle is what? Half into base is 2r into height, that is h. So exactly that is what written. And phi 2 is epsilon root 2r into pi r square. Pi r square, okay. Okay, pi r square. So this is what my phi 2 is. So total flux phi t will be root 2 epsilon r into h plus pi into r, into h plus pi into r. Okay, that is what my total flux will be. That is what my total flux will be. So that's the case, simple addition. So this then we discuss about this Gauss law. Okay, and then I give you few homeworks as well here as well. So this one I give you homework. This is again another great question. So what is this question? So we have been given an electric field, and this is a cube of L length. We have to find out the flux. Okay, total flux. Okay, the electric field in this region is, it determines the charge, total charge enclosed. Charge enclosed will be the total flux that is going out of the surface. So that is what I have written over here. So for this we have to do this double integration, which is not that easy, because here I have this curved surface, right? Here I have a bit of curved surface. So this is like this has multiple surface vectors. This is ax cap, this is a z cap, this is a y cap. Now the interesting fact is my electric field actually is only in a y cap direction. So will there be any flux produced due to this surface? No, right? It will be perpendicular, right? It will be 90 degree. No, electric field is only in this direction, right? Electric field is only in this direction. Will there be any flux produced due to this x direction? No. Will there be any flux produced due to this z axis? No. No flux produced here. No flux produced. So basically what I can say is it is 0. So I will only take care of this surface and this surface, because electric field is only in this direction. Okay, and the area vector will be either parallel or anti-parallel with respect to this. So that's why I will ignore these surfaces. I will only take those two surfaces. So that is what I have written here. Electric field is in a y cap, hence flux on all other surfaces will be 0. Okay, as theta is 90 degrees, simple as. Okay, so charge enclosed will be due to this surface, that is C G H D, and so this will be D actually, not G. And A B F E. Okay, A B F E and C G H D. This will be the two surfaces due to which the flux will be electric field, like flux will be generated. Flux electric field will cross the surface. Okay, else angle will be always 90. So I will just take these two surfaces, right? So here electric field expression I know, that is A plus By. Electric field is a function of y. Okay, it is not constant. So I cannot simply use that electric field into area that. Okay, I have to use this double integration formula now. So this is with respect to the first surface. So in the first surface, this is my electric field expression. Great. And this is my ds vector. Ds vector will be ds into the direction. What is the direction here in the first this surface, right? Okay, CG. Okay, this surface. Okay, I have actually messed up. a bit. This, right, this will be at the bottom and this will be at the top. Fine. They will just be swapped actually, because yeah, things are a bit messy here. Okay, this will also be swapped. So basically, if I check for this surface, right here, actually y, what is this like equation of the surface? Y equals to L, because this is it is in the xz plane. Y is constant, y is L here. Okay, so here I will put this in place of the electric field. I will put y equals to L. Okay, and ds will remain. And what is the area vector direction is plus ax cap, pointing outward from the volume, right? Pointing outward from the volume. So it will be plus, not ax, sorry, ay cap. Okay, so if I do the dot product, this will be just the plus, and this a plus bl will be constant because y is not varying in this xz plane. In this xz plane is y varying, y is a constant, y is constant as L. So I can simply take this out of the integration. So I will simply integrate ds. What is integration of ds? Simply the magnitude of the area. What is the area of this? It is L square. So here, that's why I have written in place of ds, I have written L square. Okay, and same for this as well. The area vector direction is this time minus ay cap, in pointing outward from the surface. Okay, so this will be minus ay cap, and this will be L square. So what will happen over here? Now I can say that simply, if I do simple computations, you will get back the answer as b L cube epsilon. This will be the total charge enclosed. This will be the total flux in crossing the surface. Okay, this is another great question. Okay, so this question I give you as homework in the last, like at the end. Same concept, right? Simply just find out, first check whether it is analytic. Yes, it is analytic, as it is polynomial. Then I will just find out the divergence, and I will find out the charge density, volume charge density. Then I can find out the Q enclosed by integrating the volume charge density. Simple as. Okay, so if I just simply integrate, integration is a bit complex because this is not a constant term. This is function of x, y, and z. So I have to take care of this. Okay, simple triple integration you can do. This I have taught you in integration chapter in calculus, in mathematics. Okay, so that was basically about the explanation part of the question. So these questions were good. If you weren't able to solve, please do try it yourself, because if I solve all the questions, no use. Trust me, it's of no use until and unless you pick up the pen and solve the question by yourself. The concept will never get into your brain. I can speak, I can shout as much as possible, but it won't get into your brain unless and until you solve the question. So it's important that you do attempt the question and not me, right? I can attempt hundreds of questions. That will only help me and not you. Okay, so let's start with today's topic. So before starting, I will just drink a bit of water. So let's start off with a question. We have to find the flux through the square sheet. Just hold on, I will just check if audio, video, everything is recording or not. Yeah, audio, video, everything is fine. Yeah, we have to find out the flux through this square sheet of area A due to charge Q at a distance d with respect to the center of the sheet. So how do we solve this? So this, right, this can actually, this particular thing, object, this particular charge will actually, the electric field lines will be something like this. Now how do I check what is the amount of flux here? How many electric field lines are crossing here? How do I do this? This we can only do with the help of a symmetry. So we will use that Gauss law using symmetry. If no electric field is directly provided in the problem and only charge distribution is given, the concept of symmetry can be applied to simplify the calculations. So first thing that you should keep in mind is that no electric field is given, electric field expression is not given, just charge is given, charge distribution is given, electric field is not given. Hence you use symmetry. Okay, this should come into your mind. Only charge is given, electric field expression is not given. When determining the flux through an open surface or any complex surface, symmetry helps in selecting the appropriate Gaussian surface to make the calculation easier. So symmetry will help us if we pick the appropriate Gaussian surface. Using symmetry, you can infer the direction and magnitude of the electric field, which helps in applying Gauss law effectively. We'll see that. Spherical symmetry, we'll use spherical symmetry for point charges or spherical charge distributions. We'll use cylindrical symmetry for line charges or cylindrical distributions. Planar symmetry for infinite plane charges. Okay, we'll do all this. We'll see. So for this particular case, right, what we will do, if I have a charge here, you have to think on your mind, how can I enclose all of the field lines? How can I enclose it? If I place a cuboid, if a cuboid is present, it will enclose all of the field lines, right? Here, top, there, left, right, everywhere, right? So how many these planes I have? I have total So this distance, right, it as it has to be symmetry, so as this is d, this top distance should be also be d. Okay, it has to be total symmetric. So how many surfaces I have? This 4 surface, 1 2 3 4, then 5 6, top and bottom. So total 6 surface, and through all of them equal field lines will go, because it is symmetry, right? It is a square, this is a square, this is a square. Okay, so phi total will be equals to charge enclosed inside the closed surface, q enclosed, that is q. So phi total equals to 6 phi, as it is equal in all of the surfaces, so it will be q. So phi will be equals to q by 6, and this will be your answer. So simple, right? This will be your answer. So the flux through the bottom surface will be actually q by 6. Simple as. Okay, you have to use a closed surface only. Here Gauss law will be valid. Closed surface, we have to choose a closed surface. Hence Gauss law will be valid. Okay, so that is the thing over here. Then only we can apply the Gauss law. So can you use the same symmetry here? What kind of symmetry is coming into your mind when you see this kind of shape? Okay, no electric field is given, just charge is given, right? What you can do, you can choose a whole sphere, right? Half of the flux will go top, half of the flux will go at the bottom. So it will be q by 2. Here this is again cylindrical symmetry. So this is at the top of the cylinder. If this was at the center of the cylinder, I could have easily said what is the flux crossing through the surface. But here, as this is half, right, I will have to choose another cylinder. So half of the flux will go through the top cylinder and half of the flux will go through the bottom cylinder. Again q by 2. Again same for here as well. Here, right, here in this case, again it will be q by 2, because I will choose another symmetrical surface in the bottom, same as this again what I can do, I can choose a surface here. Okay, again it will be again divided q by 2. But what about this? If it is placed in a corner, what about this charge? If it is placed in a corner, right, then if I choose another cube here, it is not symmetrical, right? Because this is not totally covering all the flux, because bit of the flux is going behind as well. So I have to choose a cube behind as well, and on the left hand side as well, and at the top as well, and on the right hand side or top as well. Okay, so there will be multiple cubes. So let's solve one by one. So if I do this, right, if I copy this one I have already told you the answer. So I have to choose a Gaussian surface. So what kind of Gaussian surface I will choose? I will choose a sphere. So here I will pick another hemisphere that will be upside down, and that will just close off this sphere, right? That will just close off this sphere, and again this will become a closed surface. Hence the flux will be charge enclosed, that is q. But I just want the flux due to this surface, right? Due to this surface S. Let's name it this as S1 and S2. So flux due to S1 will just be the half, because half of the field lines will go at the top and half will go at the bottom. Simple computation. So it will be q by 2. Okay, that's it. Simple question, right? Second question. So for this second question, right, so for the second question, again I have to choose a surface, right? What kind of surface I will choose? I will choose the same surface, cylinder, but it will go at the top. So it will be a cylinder, it will go at the top. Again, half of the flux will go at the top and half of the flux will go at the bottom. So in the surface S, let's name this as S1, S2. Again Gauss law I will make it valid, because this two cylinders will make it a closed surface. So flux through total flux will be q, but flux through S1 will be half of the total flux, that is q by 2. Okay. Now in the third case, what will happen? Again I will choose a pyramid, but upside down. This I will copy. Okay, next is this, and this. Okay, so here again, actually I need to find out the flux here. First I will make it close. So total, again, to flux total will be Q. Okay, but what is the flux from the at the top of the surface? It will be Q by 2, right? Because these are two pyramids, symmetricity, so Q by 2. But actually I want to find out the flux through this surface S. So how do I find out flux through this surface S? Actually there are four surfaces, same, this one behind 2 and this in front 3. So 4 times phi s will be equals to Q by 2, because this Q by 2 is getting divided in all the four surfaces, right? So my phi s will be simply Q by 8. So these type of questions can also come. They will directly ask you what will be the flux that will cross through this particular surface. Okay, so you have to use the symmetry and solve it. This will not take you much time, but you have to understand how to solve these kind of questions. So let's come back to the fourth one. If I come back to the fourth one, again I will choose the same surface as this one only to make it closed. Actually I had to do one thing, not this, different color. So this will be deleted, this will be deleted. So basically again half of the flux will go through this and half of the flux will go through this. Okay, total flux is phi total is Q only, but from this let's name this as volume 1. Okay, volume 1. So, or I can say flux at the left hand side. Flux at the left hand side will be just Q by 2, just half of it, right? Due to the left cuboid or left cube, whatever you want to say. But here I have how many surfaces? This Q by 2, right, is actually getting divided here, 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 and this surface is also there, right? This is also crossing. So total how many surfaces is it getting divided to? It is getting divided into okay, one thing you have to understand is that it will not get divided into this surface. This is not a surface, because flux will actually not cross this surface, right? Here, from here flux is generating, flux will not cross this surface. So total how many surfaces do I have? 1, I will mark this, 1, 2, behind this 3, then 4, and then the bottom surface 5. This is not a surface, this is a behind surface, right? This wherever this Q is residing, Q is just residing at the side of this 6th surface. Cuboid has 6 surfaces, but or cube has 6 surfaces, but it is just residing at that. So flux is actually not crossing it. So I will have 5 surfaces, 5. So overall my flux through any surface S, right? This surface, this is the surface S they have given me. This is, I will assume this is cube. S will be simply flux left, it will get divided into 5 surfaces equally, right, as it is a cube. So it will be Q by 10. Okay, it will not be 6, it will not be 6. Okay, 6, it will not be 6, 6 will be wrong. Okay, don't do this mistake. Here flux is not crossing through this surface, flux is actually not crossing. I have only 1, 2, 3, 4, 5 surfaces. Okay, 1, 2, this in front surface, 3, 4, and 5 surface. Okay, 5 surfaces I have. Let's move on to the fifth one. If I move on to the fifth one, now this is also another interesting thing. If I, let's say the same thing, right? If I want to compute the, again, this flux through this S surface, okay, so here what will happen, only taking this part won't complete it, right? Because this is not close. I have this flux going in the top surface as well, so I have to choose other surfaces. Okay, so this will actually be deleted, so this I have to choose. Now I will just copy this. Okay, this one top I have to choose, and also at the bottom also I have to choose, because right, this will bit of it will go at the bottom as well, so I have to choose at the bottom as well. So it is actually pretty difficult, because there will be 4 surfaces at the bottom. Okay, so this will be at the bottom, this is at the front. Okay, don't do this. This is at the front. Actually at the bottom also there will be few surfaces. The top of course there will be few surfaces. Here in front there will be few surfaces. The closed surface, these are the bottom also. So like this figure is bit messy, but can you actually identify how many surface I have? I have total 8 cubes. Okay, 4 at the bottom, 4 at the in front and 4 at the back. Okay, to cover this whole flux, because this flux will actually cover everything. I hope you are able to visualize. 4 front and 4 back. So I have 4 cubes here and 4 cubes here. Okay, so my flux total will be what? Flux total will be charge enclosed, that is Q. So my flux through a single cube will be Q by 8, because total I have 8 cubes, they will be symmetrically divided. Now the flux through this surface will be what? Here, right, if you observe, now actually how many surfaces actually it is crossing by? How many surfaces it is actually crossing by? If you observe, this surface is not crossing. Okay, no field lines will cross this surface. Okay, and no field lines will also cross this surface as well. Okay, and this top surface also will not cross. What I am trying to explain, I will explain. Actually, just let me copy this. Here, if I do one thing, okay, the field lines that will be like this, they will not cross this top surface. Okay, flux top will be 0. Again, the field lines that will be pass through this, again it will be 0. Flux whatever side this is, like this right, will be 0 due to this particular surface, right? This surface is gone, this surface is gone, and this behind surface, right? Behind surface also field lines will not cross it. Field lines will not cross it because it is just at the edge, So all these 3 edges, right, wherever the sides are present, these 3 edges, from where with whatever the we are making the surfaces, these 3 surfaces will not contribute to the flux. So flux, sorry, not sorry, it is not flux. Okay, flux behind. Flux behind, it was not intentional, trust me, it was not intentional. Flux behind is 0. Okay, flux behind is 0. So flux behind is actually 0. So here 3 surfaces are gone. 3 surface gone. Okay, only this in front, this surface and this bottom surface are there. Okay, so I have only 3 surfaces. So total flux, again this is not intentional, flux through S surface, each surface will be, it will be symmetrical. As it is symmetrical, they will all be equally divided. It will be simply flux through a cube divided by 3. Okay, so what is the flux through a cube? It is Q by 8, right, divided by 3. That is the flux through the surface. So flux through the surface S will be Q by 24. I hope your concepts are getting clear. These are actually good standard level questions. Okay, so last questions we have. This is the last question. Okay, so in this question again, this is symmetrical, these are the center, right? But in this surface, actually I have divided this into 4 equal parts. So flux in this whole side, what will be the flux in this whole right? Okay, flux in the right hand side, it will be what? Flux total is what? This is, again, it is already symmetrical, so flux total is basically Q. Okay, but flux at the right, because it is at the center, so all the 6 sides will be in action right now. So flux right will be Q by 6. Okay, so here. Now what is flux S? Flux S on the surface, with this surface, right, has been extra divided into 4 parts. All these are equal. I can observe all these are just contained diagonally. So all these are equal. So this will be flux right divided by 4. Okay. So this will come out to be Q by 24. So this will be the answer. So I hope you got the point. These are very, very good questions, and like you can do infinite number of problems on this. You can do anything. Okay. But these are few standard questions that you need to know to understand, to get into the groove, get into the level of this symmetry concept. Now just one thing, that if a surface is located either or at zero distance or at infinite distance from a point charge, the electric flux through that surface will be zero. This surface is here, ABCD, right? It is located at the surface itself. The electric flux due to this surface will be zero. Due to this point charge will be zero on this surface. Why? Because it will never cross. It is generating. It will never cross the surface, right? That's why it is zero, as explained in the previous questions as well. Okay. So I have a question. 2 point charges Q1 and Q2 are located at this particular points. Find the electric field passing through a plane z equals to 0, z equals to 20, z equals to minus 20. If Q1 and Q2 are Q1 and Q2 are 1 microfarad and 2 microfarad. Okay. So can you solve this for me? This will be homework for you. This is very interesting, like easy problem only. Just the point that I told you just in the previous slide. Do keep that in mind. Okay. Do keep that in mind. This question I am giving you as homework. Now let's move to this next question. This question: a charge of 25 microcoulomb is placed at the origin. Okay. Calculate the electric flux crossing through a portion of the cylinder as defined in the problem. So okay, this is defined here. So if I just draw the XYZ, okay, so cylinder is defined such as like this, -1 to 1. So what I can do is I can make this a bit top, that would be better. And it's a quarter cylinder basically. This is going from pi by 4. Pi by 4 is half portion only. So plus pi by 4, right? So like this, not like this. Here, yeah, quarter cylinder. Okay, so this angle, right, this angle is simply pi by 4. Okay, so although this is looking like 90, I'll change it. Actually this is looking more like 90 actually. Yeah, wow, this is good. I didn't know the iPad has this feature. That's a great feature actually. Okay, this is not straight line. I will try to make it straight. Okay, so this is pi by 4 basically, and z, this here z is -1 and here z is +1. Rho is 0 to 1. So this radius, right, radius is 1. What are they asking? The charge is placed at origin. Charge here is placed at origin. Okay, Q. Let's name this Q for now. We'll change this. So what are they asking? They are asking calculate the electric flux crossing through a portion of a cylinder. So this, through this particular surface. Now this is not a complete cylinder, right? If I make it a complete cylinder, then the flux will be through that complete cylinder will be Q. Okay, I know that. So I will do that exactly. So this is how much of a cylinder? This is actually pi by 4, right? I need 2 pi. So total, like say this is pi by 4. I need 2 pi. Actually, if I rotate total 2 pi, I will get back to my total cylinder. So number of surfaces n times s is equals to, or I can write this n times pi by 4 will give me 2 pi. So how many of these type of surfaces I need? I need 8 of these surfaces. So total flux total through cylinder, flux through cylinder is q. Okay, total charge q. But I need flux through s. That is basically, this equals to basically 8 times 8 of these surfaces I need to get a total cylinder. So this will be equals to q. So flux through that portion of the cylinder will be simply q by 8. Okay. Is this correct? Z equals to -1, 0 to pi by 4 is 25 microfarad, correct. Flux, yeah, flux through a one-way portion will be, yeah, it is q by 16, q by 8. Okay, so flux will be simply 25 micro by 8. Okay, 25 microcoulomb. This will be the flux through this particular portion of the cylinder. Now if it would have asked just from z equals to 0 to 1, then things would have been different. Okay, so let's say if it would have asked from z equals to, if the same cylinder is given but just z has been, z is changing from z equals to 0 to z equals to 1, then the answer would have been, this would have been half cylinder, right? This would have been half a cylinder then. So what would have happened is, then I have to take another surface, right? That is here as well. Okay, another imaginary surface. So then the flux through this surface would have been q by 16, that is 25 by, because what would happen, total 16 surfaces I would have required, then q by 16, so 25 micro by 16. Okay, so this will be the answer to this particular question. Okay, so yeah, that's the solution. Now like we will derive few symmetries, like a few expressions for electric field using Gauss's law. Okay, we have derived for ring charge, all those things. We'll see how easy it is with the help of Gauss law to derive expression. Okay, so how to compute, like just a quick overview summary, how to solve, right, for flux summary. Okay, so generalized expression for field. If the generalized expression for field is given, electric field is given, then you will use this d dot ds. Okay, open surface or closed surface will use this. And if our electric field is analytic, hence we can use this formula as well, that is del dot d. Okay, now if symmetry is given and only charge and surface is given, electric field is not given, then you will use symmetry. If electric field is uniform, it is constant, it is uniform, then we will use the concept of projection. Okay, we learned all these three methods. So I just give you a summary, write this in your short notes, when to use what, or you can write this in your short notes or just keep a note of it, that when to use what. Okay, if electric field is given but it is not shown, it is not uniform, okay, then you will use this generalized expression is given. Okay, and if it is charge is given, then you will use this to compute flux. If if electric field is uniform, then we'll use the projection concept. Okay, so now we'll understand the charge, the electric field due to a point charge, which we already know what is the expression, but we'll derive with respect to the Gauss law. So we know this concept, right? D dot ds equals to q enclosed, correct? So if I take a sphere, this is an imaginary surface. If I take this sphere and I write this expression, right, what will be the ds vector of this? What will be the ds vector? This will be er cap, right? This will be er cap. So I can write this, that, and what will be the ds? So always for these type of cases, right, write dl first. So it will be dr er cap plus r d theta e theta cap plus r sin theta d phi a phi cap. Okay, so now I will just replace this. What will be my ds vector here? AR cap is there, so I will just hide this thing. I will just pick the other two components. It will be r square sine theta d theta d phi AR cap, right? So I will just replace this. So this will be integration, closed surface integration of this, I don't know, okay? This will be the magnitude basically d, and I will assume uniform field. Assume uniform, because this much we have to assume that d is uniform, right? D is uniform. It is not changing. So this will become d, because d direction of d is also AR cap. That much we know. That much we know. That direction of d also will be AR cap. Okay, this much information we need to have. So dot this whole thing. What is this? R square sine theta d theta d phi AR cap equals to q. So this is constant. So I can take this out of the integration. So this whole integration will be integration of r square sine theta d theta d phi. R square can also come out, right? R square can also come out because it is not like inside. I don't have dr, so it can also come out. D phi will be equals to q. Okay. So what is this? So sine theta d theta integration from what? So I will just put the limits here. Theta will go from what? Theta, remember, to cover get a whole sphere, theta goes from 0 to pi. So theta will go from 0 to pi, and phi, this is theta actually, and my phi will go from 0 to 2 pi. Okay. So dr square 0 to pi, that is sine theta from 0 to pi is like basically it is minus of cos theta. So cos 0 minus cos pi, so it will be 2 into 2 pi equals to q, right? So your d will be q by 4 pi r square. Isn't that what we already know? So actually it's better to write this in magnitude format so that you will understand this is a vector. I am just computing the magnitude. It is better. So this is a task, but I will still do it. Okay. So we knew this, right? We got back the same expression. So my d vector will be q by 4 pi r square AR cap. I just like proved it to you, and just we deduced it. Okay, so d E vector will be what? Electric field will be what? Just I will divide this by epsilon. So q by 4 pi epsilon r square AR cap. We already knew this, but we just derived this. So it's go to derive sometimes, right? So this is how you solve this simply. Okay, so there is another way to solve it as well. How to solve it another way? What you can assume that your ds vector and your this electric field vector will always be 0. Okay, so I know that ds vector or electric field vector will always be 0. So it will be simply the area of the ds vector. So area of the ds vector will be what? 4 pi r square. Surface area of a sphere is 4 pi r square. So you can assume it like that as well. Okay, so just we know it is inversely proportional to the r square. This much we already know. What about the line charge? So for a line charge, we know we have to choose a cylindrical surface. Again, I told you, right? This is we'll choose a Gaussian surface. How am I choosing cylindrical surface? I understand that all the electric field lines that will pass through will always be 90 degrees. Always be 90 degrees. So that is what I want. That is what I want. That's why I choose a cylindrical surface. So I will choose its height as h, or this is the length of the rod. I can choose this as the length of the rod. Okay, and this is r radius. Okay, distance, let's choose this as r naught. Okay, that is a perpendicular distance from the rod. Okay. So again the same thing, I can break this D vector, like what will be the Q enclosed? Q enclosed will be equals to what? Q enclosed will be simply equals to integration of line charge, right? Because I know that it has line charge density, rho L. Okay, so rho L into D L basically. Okay, I will integrate that. Now this is uniform. Obviously we only solve for uniform cases, non-uniform cases will be difficult. As this is uniform, so this will become rho L into L simply. Okay, the length rho L into L, that's it. And what is D dot ds? Now D dot ds, there will be three surfaces, right? One will be top, one will be this curved surface, another, like only three. Okay, one will be top, one will be bottom, and another one will be simple curved surface. Okay, curve area. So this D dot ds, this is curved, so let's name the surfaces. This is first surface, this is second surface, this is third surface. So I will name this as top. Okay, let me just change colors. Bottom curve. Okay, so this D dot ds can be broken down into three bits. One is the top D dot ds plus the bottom D dot ds plus the curved D dot ds. Now from out of this, can you tell me which ones will be zero? Which ones will be zero? Obviously no field lines will be like this, right? No field lines will cross through because this point is just at the surface, right? So obviously this will be zero. Top and bottom will simply be zero. This will be zero, this will be zero. Only the curved surface will be left with. Okay, so due to the curved surface, what I can say, the angle is always 90 degrees. So D dot ds, due to the curved surface, right, the angle between D vector and ds vector is not 90, sorry, always 0 degrees. Okay, why? Simple, you can understand from here itself, right? It is always 0 degrees because if I just draw a surface vector, this is the vector, and like electric field will also be in the same direction, so it will be always 0 degrees. So I can simply write this d integration of ds because theta has gone to 0. So this will come out to be the area of this curved surface. What is the area of this curved surface? It is like 2 pi r is the length of a small ring, and multiple rings like this are there, right? So it is 2 pi rh, or I can say 2 pi r naught into L basically. Okay, this is my expression. Now this actually is equals to my rho L into L. So I can say my D into 2 pi r naught L equals to rho L into L. So my D, or I can specifically say I'm talking about the magnitude of D. Okay, that will be better. Things else you will get confused. So magnitude of D is simply rho by 2 pi r naught, and what is the direction? Direction is arrow cap. Direction is arrow cap, if you remember. So direction D vector will be simply rho L by 2 pi r naught into arrow caps. This is so simple. This is so easy, right? And if you want to write this in terms of k and lambda, if you remember the expression, it was 2k lambda by r naught into arrow cap. Okay, so this becomes so simple, right? So easy to derive. Okay, you can use the Gauss law as well to derive the electric field intensity, but obviously you have to know beforehand how will my electric field, what is the direction of electric field, that that much information you have to know. Okay, so that is the just the crux of it. So what about the sphere? Basically, electric field due to a uniformly charged spherical shell or a hollow conducting sphere. So this is hollow from inside. So inside obviously electric field will be zero, because inside there is no charge. Inside there is no charge. It is a hollow sphere. Remember it is a hollow sphere. It is not a solid sphere, right? As it is a hollow sphere, what I can say, if I choose a point that is inside, okay, that is r less than capital R. So this is R actually, although this is not looking like symmetry. So here what I can say is that my Q enclosed, right, inside when R is less than R, there is no charge here, because this is hollow sphere, everything is on the surface, this is hollow, so this is 0. Hence what I can say, D dot ds is 0 simply. Okay, D dot ds is 0. And again, what do I know? Through this sphere, the direction is in the AR cap, right? AR cap. So it will be magnitude of D into integration of ds equals to 0, or I can say okay, where did I go? Or magnitude of D into 4 pi r square, right? 4 pi r square equal to 0, or magnitude of D is 0, or my electric field is simply 0 inside. So now let's check for the outside of the sphere. What will happen? Again, I will take an imaginary sphere this time. I'll just copy and paste. I will take an imaginary sphere again, because this is a spherical symmetry. So I will take an imaginary sphere. Okay, this is not fitting here, so we'll just reduce the size of this and this as well, just to sync, just to be in sync. So I will take a sphere that is outside. So inside this imaginary sphere, right, my charge enclosed is actually Q. It is not 0 anymore. So everything will be same. The magnitude D into pi r square is this time Q. So again, magnitude of D will come out to be Q by pi r square. And what we know is that my this charge density, right, charge density is actually capital pi r square. So I can relate these two things. I can replace Q in 4 pi r square, so everything will be replaced here. Sorry, this will be 4 pi r square, 4 pi. So how can I relate? I'll show you how I can relate. So here, right, if I just replace Q is equals to sigma into 4 pi r square. So if I replace this, what will happen is my magnitude of electric field intensity, right, it will become sigma into r square by r square for small r greater than capital R. Okay, and here for small r less than capital R. Very important. So basically my electric field intensity expression will be somewhat like this. Okay, and the direction will be what? Direction will be always AR cap. Okay, here I have forgotten to write the direction, sigma r square by r square AR cap. Okay, this direction will be AR cap. You can observe that this is for a hollow sphere. Do remember, this is for a hollow sphere. For a hollow sphere, inside electric field is 0, inside flux is 0, outside the electric field will be in this fashion, decreasing parabolic fashion. Okay, so that is for a hollow sphere. It is analogous to a point charge. This particular portion is analogous to a point charge, as point charge doesn't have any inside, it has only outside. So this portion is analogous to a point charge. Logos to a point source. Okay, so now let's understand the electric field due to a uniformly perfect conducting sphere. It will be same as hollow sphere. Why? Because I have already told you that electric field, no matter what, electric field inside perfect conductor is 0. Okay, I've always told you this, right? So hence electric field will be 0 and electric field will be same expression as hollow for outside. Okay, it will follow same. Okay? For a solid perfect conducting sphere. Okay, for a solid perfect conducting sphere, you have to understand perfect, these two combination. Now I've written few points that when charges inside are embedded inside a volume of a perfect conductor, they redistribute themselves. So even if I place the charges inside the solid conducting sphere, right, perfect conducting sphere, the charges will automatically go at the surface. This is also known as skin effect. They will automatically go at the surface. They will never remain stationary at the inside the surface. They will automatically go out. So at stable equilibrium condition, all the charges will be present at the surface. None of the charges will be present inside the solid conducting sphere. Everything will spread out to the surface. That's why electric field will be 0, and this is a property of a conductor. This is a property of a conductor. This happens because a perfect conductor cannot have an electric field inside it. A perfect conducting solid sphere behaves same way as perfect hollow conducting sphere or a spherical cell. The electric field inside the conductor is 0 and all excess charge resides on the surface. All of the charges will reside at the surface at steady state. This will happen because even if I place some charges inside the surface at steady state, all of the charges will reside at the surface. Okay, now what about the electric field due to uniformly solid non-conducting sphere? Okay, this is non-conducting, or which is not a perfect conductor. Not a perfect conductor. Now for this we have to derive. Conductor. Okay, so for this I will just as it is, we will assume that it is uniformly distributed. Uniformly distributed. Okay, so if it is uniformly distributed, if I am talking about the inside surface, what will happen is that I will just choose a Gaussian surface here, a point that is lying inside this, right? So basically what will be the charge Q enclosed? It will be basically rho V into the volume of this particular Gaussian sphere, which is volume is 4/3 pi small r cube. Okay, so this will be the charge enclosed. And how will I compute the electric field? Electric field I will compute like this, that again the same formula, electric field D dot ds, okay, through the closed surface. This will be magnitude of D, as it is uniform I can take it out. This will be ds and AR cap. So what will be this? This will be equals to magnitude of D into what is the surface area of this particular sphere. It is 4 pi r square. 4 pi r square. So magnitude of D is equals to rho v is what? Rho v is actually q by 4 pi r cube, right? So this 4/3 pi will get cancelled and this will be only small r cube. I can write here small r cube by capital R cube into 1/4 pi r square. So this will come out to be, obviously I have q here as well, I have q as well here. Okay, yeah, q is here. So this will come out to be q into r divided by 4 pi r cube. Okay, so this will be the expression for a solid sphere which is uniformly distributed. Okay, so the D vector will be simply this AR cap for R less than capital R. Now if it is outside, if the point is lying outside, then the charge is fixed. This time the Q enclosed will be fixed. If I just choose a imaginary surface, Gaussian surface, it will be fixed. Okay, so it will be Q enclosed is fixed, right? What is the Q enclosed? Q enclosed will be Q only, right? Q enclosed will be Q only. So as it is fixed, what I can say outside, I can say that magnitude of D again will be Q by 4 pi R square. Okay, it will behave same as the hollow conductor, hollow sphere. Okay, AR cap. Okay, this is for R greater than capital R. Okay, so here I have written the expressions for the electric flux density. You can observe, so it will be linear because charge is also increasing, right? Charge is also increasing, so hence the electric field also will increase, and after that it will just follow the hollow sphere. Okay, so these are the few expressions that we need to know, that we need to actually, it's good to know, it's good to remember, but you can derive. This will not take you much time to derive as well, so you can derive in the examination hall as well. So the thing that I was talking, right, electrostatic shielding in the previous lecture, electrostatic shielding. What do I mean by electrostatic shielding? So here what will happen, I know, right, electric field inside a conductor will be 0. So what will happen is, as this electric field is going inside the conductor, electric field will be 0. How it will be 0? All the charges will be at the surface, hence this positive charges will actually nullify this electric field. Again they will continue after this conductor. Okay, so here inside the electric field, inside this conductor, solid perfect conducting sphere, the electric field will be 0. The electric field will be 0. What will happen basically is that electric field is flowing, right? Electric field is flowing. So what will happen? All the negative charges will get attracted here. All the negative charges will get attracted here. Okay, and all the positive charges will be here. They will get repelled, as this is the direction of electric field is this. So all the negative charges will get attracted, and all the positive charges will get repelled, right? So what will happen? This internal charges will actually generate its own electric field, right? It will generate its own electric field, that is E internal. Okay, which will be equals to, magnitude will be equals to E external, which will make the E total inside electric field equal to 0. So basically you should know the phenomena, what is actually happening inside the conductor actually. So okay, so this is happening. The conductor generates its own electric field, which will make the magnitude will be same as the external electric field, which will make the electric field inside the sphere, perfectly conducting sphere, 0. That is what is actually happening inside the sphere. It is written in textual format. When charges are embedded inside the volume of a perfect conducting sphere, they redistribute themselves entirely on the surface. This happens because a perfect conductor cannot have electric field 0. Okay, I think this has been already repeated. Sorry for this. This for some reason has been already repeated, because here, right, we have written the same thing. Search and resides in the surface. This has already been repeated. Yeah, sorry for this. This just I tried to explain the electric field due to external. It will be 0. Just the thing is, it will be 0. That's what I tried to. I think I tried to return here, but for some reason that note got gone. So here few more properties of perfect conductor are written. Under static condition, the electric field inside a solid perfect conductor is 0 when the conductor is in electrostatic equilibrium, regardless of the following situation. The conductor is isolated and neutral. The conductor has charges inside its volume. The conductor is placed in an external electrostatic field. The electric field will always be 0 at electrostatic equilibrium. So it will take some time for the conductor to be 0, like the electric field to be 0, but it will be 0. In all these cases, the charges inside the conductor rearrange themselves such that the electric field inside the conductor material becomes 0. So the charges themselves will rearrange themselves automatically on the surface of the sphere to make the electric field inside the conductor 0. Okay, or the charges inside the conductor 0. Now we'll study few misconceptions of Gauss law. So that's this portion is left. So first myth is electric flux depends on the shape of the surface. Does it depend? Does the electric flux depend on the shape of the surface? No, right? How it does not depend on the shape of the surface? Because if I choose like this Q, right? If I choose a cube surface, if I choose a cylinder surface, if I choose a sphere surface, what will be the electric flux passing through the surface? Net electric flux. It will be Q, because from Gauss's law we know phi equals to Q enclosed. So for all of these surfaces, it is only Q, because charge enclosed inside a surface is Q. So according to Gauss's law, the total electric flux depends only on the enclosed charges and not on the shape of the enclosed charges. It does not depend on the shape of the enclosed charges, only on the enclosed charges, how much charge is enclosed inside the surface. So that is what the electric flux depends on. So let's do a question on this. A closed spherical surface encloses a electric dipole. What is the total electric flux across the surface of the sphere? So what is electric dipole? Even though we haven't learned this yet, but electric dipole is a combination of couple of positive and negative, right? This I have just given you a brief overview previously as well, but we haven't gone too much into the details. We'll go into the details in the like 2-3 lectures after this. So this is electric dipole, and I have a sphere. Okay, just hold on. Can you tell me what will be the flux? Can you tell me what will be the flux of this? It will be Q and minus Q. It will be simply 0, right? It doesn't matter. Total flux enclosed in the surface is 0. Although this is actually generating an electric field, this is also generating an electric field, but this electric field and this electric field are actually overall cancelling each other out. So that's why total electric flux will be 0. Okay. So this is actually a question for the second myth, that is, if the electric flux is 0, the electric field is also 0. Actually, no. The electric field, this is actually generating an electric field here. If you observe, this is actually generating an electric field, right? If you know dipoles, right, it generates electric field. Okay, everything is terminated. Overall flux is 0 as the scalar sum is 0. Okay, it generates electric field. The scalar sum of electric field lines, because electric field lines coming into the surface and going out of the surface are same. That's why. Okay, this should terminate here. So as it is a scalar sum, yeah, electric flux is 0 here, as I am summing all the incoming and outgoing lines, electric field lines, they are 0, but the electric field will not be 0 because this has some field inside it. So that is exactly what this myth busts. According to Gauss's law, the total electric flux depends only on the enclosed charges. If the total enclosed charge is 0, this does not necessarily mean that electric field will also be 0, as can be seen here. Is the electric field 0? No, right? I have dipole, these are actually generating some electric field. This is true that total electric field lines, whatever is outgoing from the surface, is same as incoming due to this negative and positive charge. Hence, electric flux is 0, but electric field is not 0. Okay, so we cannot comment about electric field. We can only comment about electric flux in Gauss law. Good point to know. Okay, if electric flux through a closed surface is 0, which of the following statements is true? The electric field must be 0 everywhere on the surface. Is the electric field 0 everywhere on the surface? No. So this first point is wrong. The electric field may be 0 everywhere on the surface. It can be true. It can be 0 because if this inside this there is no charge present, it will not generate any electric field. So this option B can be true. This is a MSQ. Okay. Next, the charge inside the surface must be 0. The charge inside the surface must be 0. I should have said here the total charge enclosed inside the surface must be 0, which is true. The total charge enclosed inside the surface will be 0 if the flux is 0, right? If the flux is 0, total charge enclosed will be 0 according to Gauss law. Gauss law tells us this. This is the Gauss law basically. The charge in the vicinity of the surface must be 0. What does vicinity mean? So this type of language you should know. Vicinity means surrounding outside the surface. Now I will say about this particular statement that with Gauss law, I can only comment about charge inside, not outside surface. Okay, so I cannot comment about the charge, what type of charge is present outside, or is the total charge 0. I cannot comment, right? So obviously I cannot take this answer. So option B and C will be correct in this particular question, right? Let's come to the next misconception. Next misconception is the electric field at a point on a surface is only due to the enclosed charges. The electric field at a point on the surface is only due to the enclosed charges. No, right? Electric field will be due to the outside charges and inside charges, but flux will only be due to the inside charges. According to Gauss's law, the total electric flux depends here, right? Flux is very important. Flux depends only on the enclosed charges. However, electric field at a point on the surface depends both on inside and outside, because Gauss law doesn't comment about electric field, it just comments about electric flux. So to take a note that I can definitely say about electric flux, it will be only due to the enclosed charges, but electric field will be due to both outside charges and inside charges. I cannot comment about electric field. Okay, so these were few misconceptions. If you enjoyed this lecture, if your misconceptions were also clear, so like tell me, let me know, like just text me. So that's it basically for this lecture, and from the next lecture onwards we'll start a new topic, that is electric potential. Thank you for watching and happy learning.